sections throughout the entire school year that take up the bulk of, really, the entire year. The first giant section that we dealt with was triangles, and triangle proofs, and the progression sheets and stuff like that. After that, really the next big section that we dealt with was right triangles. But when in right triangles, you talked about Pythagorean theorem, special right triangles, and stuff like that. And if you think about it, the special right triangles stuff, you knew most of that from prior knowledge of Pythagorean theorem, so that wasn't anything too crazy. The circle stuff then came in, and it kind of used everything that we've done. Now, in the circle chapter, there were 8 units, or 8 sections, one of which, turn it off please, one of which I called 10.2.5, which was technically in chapter 11. Chapter 11 deals with areas and surface area and stuff. This one in 11.4 deals with circumference. Well, call me crazy, but I probably want to talk about circumference and stuff like that when you're dealing with circles, so you know what you're doing. I know, I'm asking a lot here, okay? And then after that, we got into all the other stuff. Now, what I want to do between today and tomorrow is kind of break it into half of each, and kind of hit on a couple of, or the majority of the important parts of each section that there were there, and some of the formulas that were important to remember of. And then I had made a real big review packet that has 3 or 4 problems out of each section, really, all put together. And I'll get you guys that at the end of the hour today, and I'll hope that you guys get through the first half of it, because we'll get through here this much of it today, which is like 20 questions, and then we'll do the other half tomorrow, and we'll probably have a little bit more time in class to work on that. The test then will be on Friday. I think I have it down to about 13, 14 questions, somewhere in that neighborhood. Because yeah, that's about right. But remember, you can have multiple parts. You know, you have to know how to do 2 things to solve one thing. You know, you have to use Pythagorean theorem sometimes to get through and all the other stuff. So I'm writing it out to make sure that you guys would easily finish it in probably half an hour, 35 minutes max. And then that way you've got a 10-minute buffer, so a 10, 12-minute buffer to make sure that you finish it all out. The other thing is you have to make sure you have your own calculator. I think the majority of you guys in here have that. Make sure you have the calculator that has the pi button, the multi-view, which I've been hawking since day one, so don't forget that. And also make sure the batteries are good in it. Joke, it's sold.
Whoa.
So, chapter 10. In the very first section of chapter 10, we talked, majority of what we talked about was vocabulary. And if you remember, the vocabulary stuff that we went through in section 1 kind of transcended throughout the entire unit. We utilized the vocab. If you didn't know what a chord was after the first section, you had to know what it was as you went through, because we kept using the same terms. So what I want to do is just kind of refresh your memory, if you will, on some of the vocab that we've had. Well, I didn't even do that one. What's the blue dot? The center. The center of the circle, or a circle, if you remember, is defined by a set of points that are all equidistant from a center. All those points being equidistant means that you can draw from the center to a side, and that's called a radius. Very good. The radius goes from the center of a circle to the side of the circle. Each radius within the circle they're always going to be what?
The same.
The same, good. All radii, if you will, are congruent within a circle. They have to be, otherwise it won't work. After that, the most famous part of a circle then is the diameter. The diameter is the fancy chord. I kind of skipped one by mistake here. A diameter is made up of what? 2 radii. The diameter is 2 radii. Okay? You guys all do that. That wasn't anything new. Those first bits were pretty easy. Now, we also said that the diameter was a chord. A chord was any segment that had endpoints on the circle. Well, the diameter is the segment that has endpoints on the circle. It's just the fanciest one. And it's also the longest segment within a circle. Did you know that? Yeah. Well, it has to be, don't you think? Because what does the diameter do to a circle? Cuts it in half, exactly. So the chord is the segment that has the endpoints on there. The diameter was the most famous chord of them all. I just want to go right into Rudolph. What's that? When it goes through the circle. It's secant. Remember, it's secant destroys it. Because if you go through something, you destroy it. How is that bad? It makes total sense to me. What? Secant destroy? So that's your secant. The secant is what goes through a circle. Think of it as an arrow, and think of it as a secant destroys an apple if it goes through it. It's stupid. All right, I'm fine. Try to have a little bit of fun. Yeah, apparently today's not one of them. The other one was a tangent. A tangent segment, or a tangent line, or a tangent ray. Right? A segment is tangent to a circle if and only if, or if it touches the circle at one spot, and it also has to be something to the radii. Perpendicular, it's the other one, yeah. Tangent segments are always perpendicular to radii. They will always form right angles. And we utilized a lot of that stuff before in some of the algebra problems that we had by setting things up. Let's see, what else was there? Chords, radius, diameter, secant, tangents. Pretty much it there. Now, also, after in this very first section, we talked about another term that showed up quite often. If I use theta, are you guys okay knowing that that's an angle? When an angle is at the center of a circle, what is that called? A central angle, very good. You had something that was called a central angle. The central angle had a measurement. What was it equal to? Which arc? Yeah. The central angle is always equal to the arc that it runs into. So this angle runs into that arc. So that means that your central angle is always equal to the measure of the arc that it hits. Okay? The central angle is always equal to the measure of the arc that it hits. Shh, ladies. Now, also with that, we talked about what were called major and minor arcs. Yeah. What was a major arc?
More than 180, but less than 360.
Yeah. A major arc was an arc that was greater than 180 degrees, but less than 360, because we don't go around more than once in geometry. So major arc was an arc greater than 180 degrees. The minor arc then was less than 180 degrees. We had to write them differently. How many letters did a minor arc generally have? It had 2 of them. So what happened was, was is that we would say arc BC. Does arc BC appear to be a major or a minor arc? It appears to be a minor arc. But the minute that I do this, arc BCA, that's telling me to go from B to A as the endpoints, but past C along the way. And again, this wasn't anything that took you guys more than about 10 minutes to get and not have to worry too much about, because it was just telling you directions of going around the circle. Okay? So that meant that this would have been a major arc. I tried to draw this in as best I could, but what does arc AC appear to make? So what is that called, the arc? Semicircle, very good. So the semicircle is obviously just that. It's half a circle. Just like your semi-annual clearance sale is the clearance sale that happens twice a year. Or if you go to Kohl's and every day, the lowest prices of the year, it's not always the lowest prices of the year. They just lie to you.
You have Kohl's cash.
What a scam that is. It's like the Menards rebate.
The Menards rebate is not a scam.
Are you kidding me? All right, so here's the deal. Rebates.
Yeah.
All right, after we talked about, after we did that, we also brought in, when we had our central angle, then after that, we talked about what was called an, what kind of angle is that value of x called? The x value, very good, otherwise known as inscribed, good. So the inscribed angle is an angle that lies on the circle and it still intercepts an arc. It equals, very good, equals half the arc that it runs into. So if I go back and forth between my central angle, say that this is 78 degrees. This means that you can go back and forth between central angles to inscribed angles. Now Nigel, you were all like, oh, it's only 12 questions, 13 questions, whatever. But what I can do with this is I can ask you to solve for x, but give you the central angle, which means you'd have to remember to bounce it to the arc, which means that you have to take half of the arc then. So there's stuff to this, okay? It's not just your arc, your inscribed angle is going to equal half of 78. You have to set it up, and that's the thing. And that's what we do here. We give you the ideas of how things work, but how do they interrelate? Well, that makes the arc 78, which makes your angle half of that, 36. Okay. Now also, not 36. 39, sorry. Wait, that's math is hard. Finally brought this. I just now figured out after all these years.
Midlife crisis.
Something. What would y have to equal? It's the same. Why is it the same? Turn on. Yeah. Now, guys, ladies and gentlemen, guys, angles are going to be equal to each other if they run into the exact same arc. If the two angles are both inscribed and they both run into the exact same arc, those angles will always be equal to one another, no matter what. And I think you recall, we drew one like that up on the board here, and it just had all these designs going in and out off of it. There were problems in the textbook. Remember how we had the stars inside the circles? The stars that were inscribed in the circles? Same idea. All those angles worked out being the same because they're all equal. They're all running into the same measures of arcs going around. All right. After we got into this whole arc idea of working through that, we started talking about what was called arc length, ladies and gentlemen. Hey, listen, if you guys don't want to learn or review any of this stuff, that's fine. I'll just give you the test right now. I'm fine with that, okay? If you don't care about it, fine. Just be quiet and let everybody else learn about it, okay? Thanks. Arc length was that 11.4 section that I brought into it because it worked out really well, because if you had to know something about circles, we had to first talk about what was called the circumference. The circumference is the fancy way of saying perimeter of a circle. The perimeter of the circle is the distance around it. So we defined that as circumference equal 2 pi r. Or another way that we wrote that was, well, how do you rewrite 2 times r? Nope, diameter. So this was another way we wrote it, was circumference equal to pi times the diameter. It worked either way. Now, the arc length is the distance that you walk on a circle given by some central angle. So what this is, the arc length is a portion of the circumference. So what you need to figure out is how much of the circle are you walking? Now, the reason that we have to add curvature to this is because obviously when you want to walk from point A to point B, it's usually you want to walk the shortest distance between 2 points, which would be something like that. But when you're walking on a circle, you have to walk on a curve, which makes it a longer distance. So what happened was, we got this formula. The arc length was equal to the central angle over 360. That told us how much of the circle are we working with, how many degrees of the circle, and then we just multiplied that by the circumference. Okay? And that's where we got that. We also did this in terms of when we worked with arc length. Let me put this on a clean one here. We worked with arc length. What's another name for 2 pi r? Not 2 diameter, pi diameter. This was another way of saying it was angle over 360. And what's another name for pi times diameter? Circumference. Or is angle over 360 times the circumference. So in essence, what happened with the arc length formula was that you could generate 3 different ways to write it out. And it was always dependent upon the information that they gave you. If you want to fall back on the idea that it's 2 pi r, that's kind of not a bad idea, because we know that 2r is diameter and pi times the diameter is circumference. So you can always backtrack if you need to. Excuse me. So what'll happen is you have 1, 2, 3, 1, 2, 3, 1, 2, 3. 3 parts to each one of these equations. You might know 2 of them. You might know the arc length and the central angle, find the radius. You might know the diameter and the angle, find the arc length. You might know the circumference and the arc length, find the angle. You can go any one of those combinations. And we did some of those problems before, but the problem that you guys had was using the calculator correctly. So we'll do a couple of those here in a second. But let's just go back to this diagram that I had here a second ago, and let's just say that this was 110 degrees, and we had a radius of 4. And I want to find that arc length. So knowing that I have 110 degrees, a radius of 4, that means that my arc length will equal, well, 110 over 360 times 2 times 4 times pi. Now, you guys all know that if you type that into the calculator with a fraction bar and you put it in that order, it will spit out the answer in a fraction form with pi in it. No, just leave it. What I'll always ask for is the exact answer, which means leave your answers in terms of pi. So if you do that, we get 22 pi over 9. Is that what you guys got?
Yeah.
You get 22 pi over 9, and that would be your answer for that. Okay? You don't have to hit the double arrow, you don't have to do anything like that. I don't really care what it works out to be. It's probably like 8 point something. Is that right? Am I close?
A little bit.
What is it? What is 22.9 as a decimal? Or 22 pi over 9?
7.679.
I was close, I said 8 something. But it also let you do,
Just close it and count them down.
I'm serious.
there. It also allowed you to do something like this. Come on, guys. It's enough. It also allowed you to do stuff like this, where you had, bless you, you had to find parts of it.
Achoo.
Now, when we did this problem a couple of weeks ago, the problem that you guys had with it was that you tended to write it down incorrectly before you put it to your calculator. All right? So in this one here, you're dealing with an arc length because they're telling you that that's what this is. Notice it's in inches. It is not in any degrees. If it was degrees, that means it's the arc measure. So you write out in terms of circumference. So you have your arc length, angle, 360, circumference. Well, you're trying to find the circumference, which means you just fill in the blanks for the rest. Let's see here. The arc length was 15. And then it's 60 over 360. And you got that. Well, how do you undo multiplying by a fraction? There you multiply by its reciprocal. Okay. The reciprocal of 60 over 360 is? And that'll give you your circumference. Now, that one's pretty quick and painless here. We get, this becomes just 6 times 15, and I believe we get 90. What if we changed this, and I wanted to figure out what the radius was? If I change that with the same values, but I want to find the radius instead. And this is where some of you guys had the tendency to screw up. So you know that your arc length is 15, your angle is 60 over 360, and you want to find radius, which means we're going to use 2 pi r. So, okay? Once again, the quickest way to do that is to move the fraction first. So if we multiply by the reciprocal, we just did this a second ago, we get 90, and that equals 2 pi r. Now, how do you get the r by itself? You have to divide by the 2 pi. But here's the thing. When you get to this part, you have to use the fraction bar. You have to use the fraction bar in your calculator to write that out correctly. So you get 90 over 2 pi and hit enter. And I'm getting 14 and change. Because if you don't do that, you just type in 90 divided by 2 pi. What the calculator is doing is taking 90 divided by 2 and then multiplying that by pi.
Really?
Yep.
Why?
Yeah, because that's what this says to do. It doesn't group it. If you don't have the fraction bar button, you have to type this in parentheses. You have to group it within parentheses to make it work. That's the thing, that's the kicker a lot of times with the calculators with you guys, is that you forget about how they set up when you type them in. So my suggestion, and I think just about everybody in here has the one with the fraction bar on it, always use the fraction bar, okay? If you always use the fraction bar, you're gonna be less likely to screw something up, okay? No matter what, if it's just 90 divided by 2, just hit 90 fraction bar 2, all right, and go from there. It's one of those things that you guys just tend to make a mistake on, okay? After we did that, we got into 10.3. And 10.3 talked then about chords. And more specifically, it talked about chords that were congruent. That's not even close. It talked about chords that were congruent.
So what is this?
10.3, I think 10.3 jumps into that then. In 10.3, they talked about chords and if chords were congruent. Now, by definition of a chord has endpoints where? On the circle, yeah, on the sides of the circle. So if two chords are the same length, that means what in relationship to the arcs that they run into? Yeah, those two arcs then also have to be the same. Okay? That meant that this arc and this arc would be the same. Also, if the two chords were the same length, that meant that they would be equidistant to the center. Okay. If the chords were the same length, that meant that they were equidistant to the center. Now, this looked really weird when we first talked about it, but it comes from the idea of how you measure distance. Remember, when we measure distance, we always measure perpendicular distance because it's always the shortest. So what happens is, if you get this right angle here, and then you have your chord, what are these red lines that I'm drawing? Well, the red lines. What are all those red lines that I just drew in? They're all radii. What do you know about all radii? They're all the same. So I'm just going to put V's here because I'm running out of space. And if you make a right angle, are right angles always congruent?
Yes.
Yeah. So we know that we have right angles in here. We know we have these. We also know that we have this distance from here to here has to be the same, which makes us a whole bunch of hypotenuse legs, which creates basically 4 sets of congruent triangles, which means that when you're drawn from the radius to a chord and you're right angle to it, you're the perpendicular bisector of that. That's where all that came from. So let me draw that one. Whenever you have a diameter, whenever a diameter bisects a chord, it will always, always, always be the perpendicular bisector. If a diameter bisects a chord, it'll always be the perpendicular bisector. Okay? It has to be, because the diameter cuts a circle in half, which means as you cut a chord in half and you're perpendicular to it, you become the diameter. And again, you could draw this all out and talk about right triangles. You can talk about radii, reflexive parts, hypotenuse leg to show how all that works, which comes from congruent triangle stuff back in chapter 4, back in October. So we can do all of that stuff. That's where all of these rules came from. Okay. Now, the algebra that you saw with this then really wasn't all that bad, to be honest with you. The algebra that we got from these things then was nothing more than can you identify if things wind up being equidistant from the center? Are those two chords equidistant and perpendicular to the center? Yeah, which means those two chords have to be what? That's it. And that's what a lot of this stuff stems from. It's being able to identify whether or not you set them equal to each other or we didn't have a lot of supplementary stuff in this, but you have to know some basics. I think that's about all you need to remember to get through the first half of this. Don't lose this because it's got everything you need to know.
I don't want it.
I'd like you guys to get through half of this for tomorrow.
So if someone asked to help practice, but they might be.
Thanks.
Okay. What I will do by tomorrow is I will have the tomorrow after. So you know about this one. Tomorrow afternoon I'll post the answers for this.
Okay.
Okay. So I will. I'm not gonna do that right away. That way I'm just not copying stuff down. What's that? Yeah, I'll put it up on the website. I'll just make a little PDF file of it. Just say here's the answer key, and you'll just click on it and it'll show the answers. Would you guys prefer? Would you guys like me to make a worked out solution key, or do you want to just see answers?
Worked out.
Worked out. Won't take long. That's fine. That's easy. Okay. I'll make a worked out solution key to this, and that way you guys can see it. I won't post that till tomorrow afternoon, and that way you can work through. All right.
Yes, I did.
What's that?
I said yes, I did.
I've been doing this longer than you. That's all it is.
I know your teacher for it.
It's like a language.
What's that? Yes, ma'am. Go through 20, because that gets you through all the ARC stuff that we just talked about. You should be able to get through those without too much of a hassle. All right. It's like a typical workload. It's nothing too much.
Right there, just from the top to the bottom. So I use some of that.